Assalamualaikum. Let me do the usual announcement, which I keep on doing, but seems not to have an effect, and that is attendance in this class is mandatory. Now, unfortunately, this announcement doesn't make much sense because most of the students don't pay heed to it. But these video lectures, these video recordings are not for you. These are meant for myself. So attendance in this class is mandatory. Today I would like to talk about lasers. As one beautiful application of quantization mixed with optics, with light. Now almost it's estimated that every year almost 1 billion laser diodes are sold. So this laser pointer here, this laser pointer is an example of a laser diode. This laser that you see in front of yourself is an example of a gas laser. So lasers have actually revolutionized our understanding of quantum mechanics, and they find immense applications in almost all branches of human civilization. So they are ubiquitous objects, they are everywhere, they permeate our lives. And the first laser was built around 1960 by Theodore Maiman. And the idea was presented by Charles Towns earlier. But the first idea of lasers is actually attributed to Einstein. Not precisely in the fashion of lasers, but the underlying principles of lasers were first promulgated by Einstein in the 1930s. So in order to understand lasers, so this is going to be a self-sufficient lecture on lasers and nothing but lasers today. So the idea of lasers was presented without naming the word laser by Einstein. Now, in order to understand lasers, we will have to see how photons interact with atoms. And we know that atoms can absorb photons. Photons are just light. So light is quantized in the form of packets that we call photons. So atoms can absorb photons and atoms can emit photons. And we know that the levels inside an atom are quantized. We've already seen the hydrogen atom, and we've seen the effects of quantization in hydrogen atom. We've seen spectrums from hydrogen tubes and the neon tube. So we know that levels inside atoms are quantized. Quantization means that these atoms have structures inside them for the electrons which are in discrete levels. Suppose I have a two-level system. This is a lower energy level and a higher energy level in some atom. Now what happens is, now there could be different processes when a photon comes and impinges on this atom. A photon comes and strikes this atom. What's going to happen? Now a photon is defined by, so this is how I would represent a photon, by a wiggly line. And this photon will have a certain frequency, f. This frequency determines the color of the photon, the wavelength. Since these are massless particles, the frequency and the wavelength are related by this relationship. F times lambda equals the speed of light. The photon is moving with the speed of light. That's light speed. Now this F comes in, and the photon, the single photon, could carry an energy hf. So F determines the energy carried by a single photon. Now this energy separation, delta E, in two levels that we're focusing our attention on inside the atom, could be different, or it could be the same as the energy of the incoming photon. So we can tune this incoming energy to an energy gap inside the atom. And this incoming energy could be also detuned. So we can choose this frequency, and we can tune this frequency to actually be equal to this energy gap, or it could be wildly different. So depending upon whether this incoming photon is tuned to an energy gap, we can have different kinds of effects. Now suppose that this is a situation, and we have an electron inside a lower energy level. Let's call this energy level A1, and let's call this energy level 2. So this delta E is really E2 minus E1. Now suppose that initially, before the photon has come and struck the atom, the lower level is populated, which means that I have an electron sitting in the lower level. So what could happen is that if this HF is detuned from this delta E, this photon will pass unscathed. It will just pass through the atom. The atom will be transparent to the photon. However, if this frequency is tuned to this gap, it's possible that this atom will absorb this photon, and as a result, since the photon carries energy and the photon has now been absorbed, all of this energy must be transferred to the atom, and as a result, an electron will make an upward transition from the lower level to the higher levels because of this tuning. The incoming photon is in resonance with the energy level inside an atom. We have nudged the atom with a frequency that matches the frequency of the atom. There's complete resonance. So this process will excite the atom, and this process, of course, is called absorption. So now the atom is acting like an absorber of a photon because the incoming frequency is precisely tuned to an energy separation inside the atom. So this is one kind of process that is observable. Now let's look at another process. We have the same energy levels, 2 and 1. And now we start off, the initial condition is such that the electron is already in an excited state. The electron has already been promoted to the higher level by some means in the past. Okay? So at time t equals 0, this is our state. Now what could happen, like any other system, the electron would like to fall down to its lower energy levels so that the atom becomes more stable. Everything would like to fall into a state of equilibrium, which means that the atom would like to equilibrate its energy, it would like to lower its energy. So in the process of lowering its energy, this electron falls down to the ground state, and in the process it emits a photon, HF. And this HF exactly matches this energy separation. So a precise frequency is emitted, and the atom is now acting like an emitter, and this process is emission. Now since there is nothing that is telling the atom to emit a photon, it's just the laws of equilibrium, the laws of thermodynamics that are dictating that the atom comes back to its ground state, the process is spontaneous. It happens on its own. There is no need for a catalyst or something external to the atom to nudge the atom to come to its ground state. So the process is also called spontaneous emission. Now this frequency is precise. We looked at the line spectrum the other day. There are precise wavelengths, precise frequencies that are emitted that are representative or a signature of the energy level separations inside the atom. This process is absorption. Now the laser is actually in an atom which lasers. lasing is also used as a verb, by the way. The atom that lases, that gives off radiation, in all of these atoms, absorption is taking place and spontaneous emission is taking place. Both of them are working in tandem. Both of them are working together. But above that, beyond that, Einstein proposed a third process. And that third process is something quite interesting. Now I have the same two-level system. An electron is in the excited state, and it's sitting there in the excited state, and a photon comes in, HF, whose frequency is tuned to the energy separation between these levels. Now what this incoming photon can do is, according to Einstein, it could stimulate the downward transition of the electron. So now instead of absorption, an atom is already in the excited state, and an incoming photon triggers the downward transition of this excited electron, and in the process, since this electron has fallen down in its energy, it emits a photon. The atom emits a photon of precisely the same energy, HF. Energy has to be conserved. And this incoming photon, since energy still has to be conserved, it also passes through this atom. Nothing happens to this. It just triggers or catalyzes or seeds the downward transition of an already excited electron. This downward transitioning electron emits a photon, and this incoming photon is retransmitted, and both of these photons, the retransmitted photon and this photon, have the same frequency, which is matched to the gap. Now one photon comes in and two photons go out. This process is called stimulated emission. Now it's absolutely essential to have this third process. Now one might wonder, why do we have this stimulated emission? Of course, first of all, this is a feasible process, which means that this is a legitimate process. It is an allowed process, it's a legal process because it conserves energy. Right? There is no violation of conservation of energy. Energy comes in, energy goes out. The same amount of energy goes out. This atom is making a downward transition, so it's falling in favor, its energy goes down and it emits a photon. So energy is conserved in the process. Hence, it's a legal process. But you might argue, why do we need this? How do we know that this process is taking place? We need thermodynamics to explain why do we need a stimulated emission. And that's what I'm going to do now. So now we have three processes: absorption, spontaneous emission, and stimulated emission, all working hand in hand. And this is actually the requirement for a laser. It shows that one photon can stimulate the emission of another photon whose frequency is matched with the frequency of the incoming photon. And the nice thing is that both of these photons are moving in the same direction, which is the initial direction of the incoming photon. Every photon is going to have momentum k, right? Which shows the direction of propagation of the photon. Light moves in a straight line. So these two photons are re-emitted in the same direction. So there's some directionality in this emitted radiation. So we have directionality. In laser parlance, this is called collimation. The radiation that is coming out from this atom is collimated. All the photons are moving in the same direction. These photons have the same frequency. So this light is monochromatic. One frequency, one color. But you can take, you can always take an ordinary light and collimate it. You can take a light bulb, for example. This is emitting light. You can put a screen and a pinhole, this pinhole is going to produce a collimated beam of light emerging from the other end, which diverges a little bit, but still it's more or less collimated. Laser light is also divergent to some extent, but you can have a directional beam from an incandescent bulb as well. So how is this light different from an incandescent bulb? We can have monochromaticity. For example, I can put a filter here that filters out all wavelengths and just passes, say, a particular wavelength, 633 nanometers, for example. So still I can produce a collimated and a monochromatic beam with a light bulb. So how is this light bulb acting differently from a laser? There is a third property which makes a laser special, and that third property, in addition to directionality and monochromaticity, is coherence. Now what is coherence? Coherence has two meanings. The first meaning of coherence is temporal coherence. Temporal coherence means the following. If I have the time axis here, what is light? Light is just an electromagnetic wave. It's an oscillating electric field. Okay? So now if I have laser light, which is by definition the ultimate coherent source of light, and if I take some point in space and I look at the electric field is oscillating. It's going up and down, up and down. So with time, at a certain point, the electric field is oscillating with time. Now this is a perfectly temporally coherent oscillation. Now how do I describe coherence? In order to describe coherence, I would actually try to define what is meant by incoherence. Okay? If I describe incoherence, you'll actually know what is coherence. So this is a perfectly coherent beam. If instead I have an incoherent beam, what the incoherent beam does is that after a particular amount duration of time, it switches its phase. So the phase switches. So there are abrupt discontinuities in the electric field after some intervals of time. So this represents a beam that is only partially coherent. Its coherence is maintained for this time, and then it switches its phase. Then its coherence is maintained for different interval of time. Let's call this interval of time tau 1. Let's call this interval of time tau 2. Let's call this interval of time tau 3. So it's switching its phase. So this beam is only partially coherent, but it's incoherent. A laser, a perfect laser, is temporally coherent with a long average coherence time. If I take the average of all of these times, when n is the total number of intervals I'm considering, and this is called the coherence time of the laser. A laser has a long coherence time. The phase remains pure. There is spectral purity. The phase does not switch. It does not make these discontinuous jumps over and over again. Temporally, on a time scale, the laser maintains its phase coherence. This is what is meant by temporal coherence of a laser. And this is an essential property of a laser. It must have a long coherence time. The second property it must have is spatial coherence. Now in spatial coherence, you have the same idea on a length scale. So if I have a laser beam, and laser beam is coming out from a laser, and I draw this hypothetical line here. So this is a plane normal to the direction of propagation of light, and if I look at all of these photons, the photon at the top of the beam, the middle of the beam, and the bottom of the beam, all three photons, they have the same phase. Likewise, I can draw any other line I can draw a wavefront, in other words, a plane that is normal to the direction of propagation of light. And all of these points are in phase. This is spatial coherence. Looking at it differently, if I take 2 points on this beam, any 2 points on this beam, and the distance between these points remains fixed, say x, then as the beam propagates, the phase difference between these points over this distance remains fixed. Whatever the phase difference, the phase is going to change because this beam is oscillating, but the phase difference between these points is always going to remain constant. So if the phase difference between these points is delta phi as a function of this distance x, then this delta phi is constant over length scale. So I'm taking two distant points in the laser beam and they always remain phase coherent. They remain the constant phase difference. The phase does not change between these points. The phase difference does not change. This is spatial coherence. So it's important to have spatial coherence. That's why you can actually see interference patterns. If you don't have spatial coherence, we cannot see an interference pattern. Lasers have a degree of spatial coherence, which could extend from centimeters or up to meters. For example, if I were to perform a double slit experiment, then light that comes out from this slit and light that comes out from this slit, these two light beams must maintain a constant phase difference. That's why you'll be able to see an interference pattern. If the phase difference between these points in the light is constantly changing, the interference pattern is going to be washed away with time. And we ensure, if we don't have lasers, we can ensure coherence by having another pinhole and an incandescent bulb placed here, which is emitting light. Now I'm making a point source out of this slit. And since this is a point source, these beams are essentially coherent with one another. So this slit is actually ensuring coherence. Coherence is the hallmark, or it's a prerequisite or a necessity for observing an interference pattern. And what I have in front of you is I would like to show you an interference pattern. So what I would like to show you here is two kinds of experiments, basic experiments. Any questions up to this point? You had a question? Good question. Excellent question. So my friend has asked, if an electron comes down from an excited state to a lower state, why does it have to emit a photon? Well, it's not necessary to emit a photon. There are certain transitions that are radiative. Radiative transitions emit photons, but if an atom is in an excited state, it collides with another atom. It can still be de-excited without the emission of a photon and only the generation of heat. It could produce phonons, it could produce vibrations in the crystal. So it's not necessary that only a photon is emitted. Other forms, other channels of energy degradation are also possible. For example, you can heat the solid. You can emit waves. The solid can start to oscillate. This is called a phonon, which are quantized oscillations. So there are radiative transitions and there are non-radiative transitions, and both of them are important. Alright? So it's not necessary that only a photon is emitted. So the two kinds of experiments that I would like to show you are the following. First, in front of you, I have an arrangement. Can you turn this on? So this is a slit. And it's just a single slit. I'm going to turn this on so that I can actually zoom into this. So this is a narrow opening between two blades inside this. So if you observe here, alright, so you can observe a slit, and this is a micrometer. If I rotate the spindle of this micrometer, this slit can be opened and it can be closed. So I can change the slit width. So now I'm closing the slit, okay, by turning this screw here. Alright, so this is my slit. The slit can be opened, and opening the slit, and it can be closed. What I would like to do now is I would like to pass laser light to this. And using the coherence property of light, I would like to see if I get an interference pattern. Okay? This is what I would like to do now. Now what I have in front of you here is a gas laser. This is a helium neon laser over here. And it emits red light of a particular wavelength, 633 nanometers. Okay? And today we're going to see how this laser actually works. But before that, I would like to demonstrate this property of a laser, the coherence property of a laser. And in the process, I would also try to demonstrate the uncertainty principle. That is, the slit width determines the kind of interference pattern that you observe. So what I'm going to do is, I'm going to open up the slit completely. And I'm going to place it in the beam path. So first of all, I'm going to do a basic alignment. I'm going to see the laser, the height of the laser. It's around 13 centimeters. The height of the slit should be almost the same. So this is a bit higher. So I move this down a little bit. The slit is completely open. On the other hand, alright, so I turn on the laser. I do a bit of alignment. After I turn on the laser, I will have to do a second step of alignment. The laser is on. I turn on the shutter. So the laser beam is not actually passing through the slit. So I have to change the orientation of the laser a bit. This is Ali Hassan's business card. Alright, so you can see that the laser beam is passing through the middle of the slit. And what I observe on the other hand, on the other side, is just a blob. Okay? I can turn down the lights a little bit. And now what I would like to do, I would like to slowly close the slit. Right now there is no diffraction observable. Okay? So it's just, the slit width is too large for diffraction to take place. I'm closing down the slit, and if my laser beam is coherent, over the dimensions of the slit, I will be able to see an interference pattern. A single slit interference pattern in this case. Let's see. Can you zoom in? I can actually see with my bare eyes a very nice interference pattern here. Zoom in. Or zoom in. Come. But zoom out. All right. Now here what you can observe is, so this is central maximum, a big central maximum, which is the undiffracted spot. And then if you observe carefully here, there are regions of bright intensity followed by regions of dark intensity. There's a dark region here, a dark region here, a dark region here. So this bright, dark, bright, dark, bright, dark. This is the typical interference pattern from a single slit. Now if I change the slit width, I can change the spacing between the two dark regions or two bands. I can change the width of the different bright and dark bands. And let me show you how I can do that. So I can change the position of the screen, and the beam, since it's diverging, I can see more vivid effects. If my screen is placed further away, I can actually see a more vivid effect. Front zoom in, please. Alright, now this effect is actually clearer here. I have a central dark, a central bright spot which corresponds to the central maximum, the central low, followed by a dark region. Now what is dictating the photon shouldn't reach here? It's the interference, it's the coherence of the laser beam that is actually telling that destructive interference is going to take place along this beam path. Along this beam path, very little photons or hardly any photons reach this point on the screen. Likewise, there is a dark fringe here, and brightness in between. So this is a typical single slit diffraction pattern. If I change the width of the slit, this pattern is going to change. Now let me try changing the width of the slit. I'm changing the width of the slit. Now, can you guess whether I am decreasing the width or increasing the width? I was decreasing the width of the slit. Decreasing the width of the slit made the beam, this central maximum, the minimums of, after the first central maximum went further apart. The central maximum dilated, it expanded. As I close the width, the fringes dilate, they expand, they go further apart. This is the uncertainty principle, because what I really have is the fanning of the momentum vectors of the photons is going further and further apart. Delta P is going up as I'm decreasing the slit width. Delta X is going down, delta P is going up. So this is a vivid demonstration of uncertainty principle. The uncertainty principle, by the way, is not just quantum mechanical, it applies in the classical world as well. It just comes out from the wave-like properties of these radiations. So I can change the slit width further. Now it's a thinner, it's a tighter slit. Tighter slit means delta A is reduced and delta P has gone up. So the photons that are making the central maximum, they fan out in larger directions. The uncertainty in P has gone up. Okay? So this is an extremely narrow slit. Now let me go the other way around. So now I'm opening up the slit. The central maximum is becoming thinner and the interfringe distance is decreasing. The fringes are getting closer and closer and closer together. Now if lasers were not coherent, I do not have a slit before the two slit apparatus. I just have a single slit. If the laser was not coherent over the width of the slit, I would never see a diffraction pattern or an interference pattern. Interference and diffraction are one of the same thing. Now I'm opening up the slit. Now the slit is so open, so largely open, that the width of the slit is much larger than the order of the wavelength, and the interference pattern or the diffraction pattern disappears altogether. Okay? Now let me do this experiment with another device. The second kind of device I would like to do this experiment is a double slit. So I turn down the shutter, I remove this object, and now I have a strange kind of object here, okay? So this object here, can you zoom in a little bit? Okay, that's good enough. So this is a razor blade which has been cut into two, and the two distal parts, the parts that were on the outer periphery, have been joined together, have been placed such that they face one another. So a slit is formed between the two halves of the razor blade, and inside the slit I have placed a pin, a common pin. Okay? So I have this kind of arrangement. I have a slit formed by two halves of a razor blade, and inside this slit I have a pin. So I have actually tried to make up a two-slit pattern, a two-slit geometry. So now I would like to repeat the experiment with this two-slit arrangement. You can actually, I've uploaded, yesterday I've uploaded a micrograph. I've seen this under a microscope, and I've uploaded a photograph on my website as well. I place this two-slit pattern inside the beam path. I do some basic alignment. Okay, let me turn on the laser. Never stay directly into a laser beam. And what I immediately observe is an interference double slit pattern. Okay? So this is a classic double slit interference pattern. And if you are, I don't know if you can see the screen directly, it looks quite pleasant to observe on the screen directly. Okay? So this is double slit interference. Double slit interference will have a different intensity profile than a single slit interference. Unfortunately, I cannot change the slit width in this experimental arrangement. So what's happening here is that the laser light is coherent over the distance of the two slits, which is about 1 centimeter. So the coherence length is at least 1 centimeter. In fact, for gas lasers, the coherence length can be of the order of tens of centimeters. So I move this screen a bit further so that the fringes appear more clear. Okay, once again I have a central maximum, and I have a dark region here, a bright region, dark, bright, and I can take a picture of this. If you like to take a picture of this, you can then use a software, for example, ImageJ, to plot an intensity profile. I have a big central maximum, a dark fringe, small lobes, and the intensity of the lobes is waning down. It's going down as I go further out from the central maximum. So this is what I like to demonstrate today. Let's move on back to a discussion of lasers. Yes. No. Only in a diffraction gradient, which has a large number of slits, can you expect the intensities to be the same. Any questions about this? All right. Yes. Well, if you look at a butterfly wing, for example, or a moth wing, the butterfly wing or a feather of a bird has these slits. So the butterfly wing will appear different depending upon the orientation of the slit. So you do see this effect, which is called iridescence. If you take a CD, a DVD or a CD, and just glance light on its surface so that there is grazing angle of incidence, then you will see green and red and blue lines that are forming on this CD because there are tracks on the CD which act like a normal diffraction grating. So you can see this iridescence effect, as it is called, in real life as well. That's not a problem at all. Okay, so let's carry on with this discussion. For lasers, we've demonstrated that we have the property of directionality, monochromatic coherence. We haven't talked about lasers as yet. We've only talked about stimulated emission. So how do we form a laser? What's the construction of a laser? And what are the requirements of a laser? Now I would like to do a bit of foray into mathematics here. And I would like to introduce to you the concept of statistical mechanics, thermodynamics. Now we have three processes here: absorption, spontaneous emission, and stimulated emission. By the way, one philosophical concept is there is no such thing, some scientists would argue, there is no such thing as spontaneous emission. We only have two processes, absorption and stimulated emission. And spontaneous emission is really stimulated emission by vacuum photons. You don't need to understand this fully, but if I have vacuum here, vacuum has some 0 point energy, some ground state energy. That ground state energy, the photons of vacuum are stimulating the downward transition in a spontaneously emitting atom. But this is just an A slide. We don't need to understand all of this. So let's do a bit of task. Similar to what Einstein did. So you're actually reproducing Einstein's calculations. Only from about 90 years ago. That's not a problem, but still, these are Einstein's calculations. So we have three processes here. 1, 2, and 3. Now if you look at absorption, and I would like to define a rate of absorption. How many photons are absorbed by the atom per unit time? Now what would this rate depend upon? Just look at this diagram. If I would have a gas of atoms, a large ensemble of atoms, a large number of atoms, and I would like to find out how many absorption processes are taking place per unit time, what would this rate depend upon? Yes? Okay, suppose there is some energy gap. If I have atoms already in the excited state, would absorption take place? No. So I need atoms in the ground state. So more the fraction of atoms in the ground state, more higher the number of atoms in the ground state, higher will be the rate of absorption. So this R absorbed will depend upon the number of atoms in the ground state, 1, N1. What else would it depend upon? Yes? How exactly, very good. How many photons are available at the right frequency to stimulate this absorption? I need photons inside my cavity. So wherever atoms exist, I need photons around. I need the atom to be bathed by photons of the right frequency so that absorption can take place. So I need some density of photons. Let's call the density of photons rho. Rho is the number of photons per unit volume of the right frequency. F, precisely F. I need photons. So photons are my stimulants. They are absorbed. If I would talk about the rate of absorption, I need photons to start off with, and I need atoms in the ground state. So my R depends upon rho and N1. And there has to be some constant of proportionality. Let's call that constant of proportionality B. And I'm going from 1 to 2. So this is B1, 2. 1 to 2. So this is my rate of absorption. Any questions about this? Simple? Yes? Photons of light, which are being absorbed by the atoms. Per unit volume of space. So the atoms are living in some space. I can have photons. I need to find out the number of photons available per unit volume, so that I need to normalize things. Excuse me, there's a class going on, and I'm trying to make an effort here. So this is the rate of absorption. What about the rate of spontaneous emission? Let's look at this process there. Now what would this depend upon? What is the analogous relationship for spontaneous emission? Number of atoms in the excited state, N2. What else? Does it depend upon the number of photons available?
No.
No. So it doesn't have a rho factor. It just has a constant of proportionality. Let's call it A. A and B, because Einstein used these symbols. Okay? So we are treading the path Einstein tread in the 1930s. Then we have the rate of stimulated emission. Now what does this depend upon? Can you speak up? So here is the process here. This is the process.
So rho F.
Rho F, I need photons of the correct frequency, the density of photons. How many do I have available to stimulate the emission process? What else? Number of atoms in the excited state, N2, and some constant of proportionality, which I call B21. Now these symbols are swapped. Absorption is also called stimulated absorption. So both of these require photons. Absorption and stimulated emission require photons, but spontaneous emission doesn't require the presence of nearby photons. So I have one process that accounts for absorption and two processes that account for emission. Now in a state of equilibrium, if no photons are absorbed or emitted, in equilibrium, that's what equilibrium means, the rate of absorption is the same as the rate of emission. So in equilibrium, of course in equilibrium we can't have emissions, we can't have laser that doesn't, a laser can never operate in equilibrium. I'm going to prove this fact. So in a state of equilibrium, the absorption and all the two kinds of emissions, they are equal. The rates are equal. Whatever comes in goes out. So there is no exchange of energy between the atom and the photon. Therefore, in such a condition, I will have rho F N1 B12 equals AN2 plus B21 rho F N2. Okay. Now what I would like to do, I would like to make rho the subject of this equation. So this is our first foray. We're putting our foot into the world of statistical mechanics. Thermodynamics. Microscopic thermodynamics. Rho F N1 B2 minus N2 B21 equals A N2. Rho F An2 N1 B12 minus N2 B21. Now I divide both sides by N2 A B12 N1 over N2 minus B21. So in a state of equilibrium, we have calculated the density of photons. Yes. So I have a cavity. A box. Okay? And I have an atom inside this box. A two-level atom that is acting like an absorber or an emitter. And I have photons inside this box. Now rho F is the density of photons in the vicinity of the atom. This atom is absorbing photons or being stimulated or stimulating emission by the presence of photons. So both the absorption and the stimulated emission, they are triggered by the same bath or soup of photons that is nearby. That's why we have the same rho F. Now if you look at this expression, Einstein came up with this formula for the density of photons per unit volume. How many photons exist per unit volume of the correct frequency? Now, before Einstein, there was another scientist who's credited with the invention. I don't like to call Its invention, the invention of quantum mechanics. In fact, it's the discovery of quantum mechanics, but invention is glorifying his contributions. He invented quantum mechanics, and his name was Max Planck. So Planck, at the turn of the 20th century, around 1901, came up with an independent calculation of rho f. We might have time to look at his calculation, but for the time being, let me state his result. In fact, the derivation of rho f by Planck is actually profound. It actually teaches you a lot about quantum mechanics. But let me, at this juncture in our course, just state out the result. This is probably the only time that I'm going to present the result without describing its derivation. I might do it later, but for the time being, let me just throw out the result. Rho f, according to Planck, is given by 8 pi f squared over c cube h f over e h f over k dt minus 1. At this point, let's take a 10-minute break, and we're going to continue with the discussion of this.